Okay, good afternoon, everyone. Welcome to today's webinar. We have Dr. Efthymios Balomenos from Greece. Efthymios studied mining and metallurgical engineering at the National Technical University of Athens in Greece, and he received his PhD in thermodynamics in 2006. From 2008, he has been working in the laboratory of metallurgy as a postdoc researcher focusing on sustainable process development, CO2 mitigation strategies, exergy analysis, and resource utilization efficiency. He was involved in research management in a number of companies, and he has more than 40 research publications in journals and conference proceedings, with more than 500 citations and an H index of 13. Since 2013, Efthymios has been working for the Metallurgical Metallurgy Business Unit, focusing on sustainable solutions for the valorization of bauxite residue. My name is Elias Matinde. I'm a senior researcher at Mintech. I'll be chairing this meeting. So I'd forgotten to put my video on so that people could see me. So I'll be chairing this webinar. Just a number of rules. I would propose that if you have got questions, please put them in the chat box, or alternatively, you can wait at the end of the presentation so that you can raise your hand, and then Efthymios can address them. Over to you, Efthymios.
Thank you very much for this nice presentation. Welcome all the attendees. I will be presenting on my experience in scandium and rare earth extraction from bauxite residue. Let me start by sharing my screen. So I'm hoping that you are seeing this presentation, right?
Yes, I can see. I'm sure everyone else. Yes, please go ahead.
Okay. So as I said, this is basically sort of 10 years experience in trying to valorize bauxite residue, which at some point led also to rare earths and scandium extraction. Yeah. So the subject is on rare earths and scandium. I like to open this a bit with what is scandium, because usually people are not so much aware of this element. This element is considered a rare earth, although some geologists might debate over it. It is, in fact, a bit more rare than the other rare earths. As you can see, it's situated in the periodic table above yttrium, which it has its closest connection with yttrium in terms of properties, and it sort of distance itself from the lanthanides, from the rest of the rare earths. And this is the problem, because in nature you don't find it combining any type of minerals. So it is widely dispersed. It's, as you see, the 36th most abundant element in the crust, but you will never find it in concentrations exceeding some parts per million. And this is a problem. And you also will not find it necessarily along with the other rare earths. So that is why its behavior is a bit different from the other elements in this group. But it's very interesting, because as you can see, it has superpowers. It is in fact a replacement for yttrium. It can replace yttrium in most material applications, providing better results. And most notably, the case of the solid oxide fuel cells, where when yttrium stabilized zirconia, which was the solid electrolyte layer, was replaced with scandium stabilized zirconia, this allowed to lower the operational temperatures by 300 degrees, making this solid oxide fuel cell technology viable to be commercialized. And at the bottom of the screen, you can see some of the solid oxide fuel cells based on scandium electrolytes, which are currently being deployed by the company known as Bloom Energy in the US. So efficiently, these are converting natural gas, these boxes that you see, into electricity that powers the building and the servers and so on. Also, scandium can replace yttrium in garnets, producing better lasers, and it is used in high-density natural lights because it goes close to a solar optical spectrum when used in such lighting. More importantly, scandium goes very well with aluminium, and the scandium aluminium lithium alloys are a bit of a nice history behind of them, since they were used in MiG aircrafts back in the 80s, allowing the MiG-29 to use welded aluminium structures, making it much more lighter and maneuverable in the air, giving it a distinct advantage during the Cold War. So what does addition of a few percent of scandium into an aluminium alloy does? You can see that it increases sufficiently the strength of the aluminium alloy just by adding 0.1 to 0.2% in the alloy, and it reduces hot cracking during welding. So it basically hardens your aluminium alloy, especially the aluminium magnesium, the 5000 series, has an amazing increase with just a small addition of scandium. And so the future for scandium, with two types of applications, especially the solid oxide fuel cells and the use of the aluminium scandium magnesium alloys, which can be used even in 3D printing applications, are expected to increase by 30 times its demand in the next decade. And to understand why this is very exciting, here is the picture of a 3D printed Airbus frame where they used this scalm alloy, aluminium scandium magnesium alloy, to build a frame that can fit into an Airbus. And this partition weighs 45% less than the partition currently used by Airbus. So you can imagine that with scandium aluminum alloys, you can expect huge energy savings and fuel savings. But scandium, as I said, is a very rare earth, and these applications are only emerging now. And in fact, the global supply of scandium is around 10 to 15 tons per year, not 1,000 tons, just tons. So it does not even fill a truck, right? It's a very small amount, the global supply of scandium, and the global demand, which is a bit higher than supply. The value chain of scandium is insanely expensive. So 1 gram of scandium oxide, just of 99% purity, could be charged for $1. And the metal, scandium metal, could be even $200 per gram. And more importantly, the aluminium scandium master alloy that is used to make this magnesium 3D printing powders is valued between $100 and $150 per kilogram. Scandium is not traded in the markets, so all these prices are very volatile and very uncontrolled, and they depend on trading deals between the parties involved. So where is scandium produced? Scandium is produced in all deposits in Russia, in Ukraine, which were used for uranium mines. There is a scandium also mine in Kazakhstan, but main sources other than these legacy, let's say, sources include some rare earth production in Bayer Obo and Kola and Ishla, and several acid waste facilities from titanium dioxide production. So as you can see, the main production of this rare earth element, again, is located in China, followed by the former Soviet Union. But where else can we find scandium? And this is focusing now in the topic of this presentation. We can find it in bauxites and nickel laterite ores. And these seem to be the most promising scandium resources for future and large-scale production. The nickel cobalt laterites, especially for those found in Australia, seem to have the advantage currently because they can be a source for both nickel, cobalt. These are extremely valued elements now with batteries, and with the same flow sheet, with the same processing, hydrometallurgical processing, you could extract even scandium. So these seem to be the most viable, the next step in the scandium production. But at the same time, you have the bauxites that are used for alumina production, where scandium is enriched in the bauxite residue. It's not lit during the Pyro process. So all the scandium ends up in the bauxite residue, having essentially doubled its concentration from the initial ore. So there are bauxite residues in the world which have several hundreds of ppm of scandium. Notably, Rusal has already produced a pilot plant for extracting scandium from bauxite residue. You can see here an indicative estimation of the concentration of the scandium in the various sources, and also the estimation of the reserves. As you can see, while the nickel cobalt laterites could have very high concentrations, they lack in reserves. The same with the titanium acid wastes. So, bauxite residue could be a resource for scandium and for other rare earths. As I said before, during the Pyro process for the aluminum production, scandium and all the other rare earths are basically concentrated 2 times comparing the initial bauxite ore. The bauxite residue, if you're not familiar with the alumina cycle, the alumina production cycle, is basically what is left from the bauxite ore after you have leached out the alumina in the Pyro circle, in the alkaline soda solution of the Pyro circle. Each year, we are producing more than 140 million tons of bauxite residue, as essentially bauxite residue is produced on a 1-to-1 molar mass with the alumina. In the European Union, we have a production close to 6 million tons per year of bauxite residue, and there's very little reuse for this residue. It is stockpiled in landfills or dams. The old practice was to pump it out as a slurry as it comes out of the process and make huge dams or lakes, and hence the name that most is usually known for this residue is called red mud, as its color is very red due to the high iron content. But more modern approaches into bauxite residue handling include filter pressing, as you can see in this picture from our plant, where the bauxite residue is now a solid filter cake. Depending on the origin of the bauxite residue, and of course the origin of the original bauxite as well, you can see various values of scandium in grams per ton for different sites, production sites. As you can see, in Russia, they have very high levels of scandium, and so does also Jamaica, Greece, and China. So in our case, the bauxite residue contains 70 to 100. It could contain even more, up to 130 sometimes, of scandium. I have to explain this. This is largely dependent on the initial mix of bauxite ore used in the plant. So in the past, like 3 or 4 years ago, we were having much more Greek bauxite into our feed. Now, the last years, we have a bit more tropical bauxite feed into our mix, and therefore the amount of scandium has dropped. The scandium is located mainly in the Greek bauxite that we're using. There has been several studies, including PhD theses, that have located that scandium in this particular residue coming from the Greek bauxite is associated with the mineral phases of iron. So it's within hematite and goethite phases. You can see on the right hand of your screen, you can see the composition of the bauxite residue, which is 40% iron and 60% alumina, followed by silica, calcium, soda, and titanium oxide. And then you can see in parts per million the concentration in some trace elements like cerium, lanthanum, yttrium, and scandium. As you can see, there's a lot of about another 100 ppm of neodymium are there as well. It's not inside this table. Also you can see the mineralogical analysis of the phases of the bauxite residue. The left side is the phases that are there from the initial bauxite ore, leftover not leached phases. So mainly some leftover alumina phases, followed by iron phases and titanium phases and calcites and quartz. And then you have the new phases that are formed during the Bayer process that are secondary precipitations like hydrogarnets, concrenites, perovskites, and so on. And gibbsite is obviously alumina that precipitates out of the solution before we have a chance to separate it. So each year we produce in our site close to 800,000 tons of bauxite residue. And the big question now is, how can we extract scandium from these resources? The challenge here that we're facing is that we have to extract 100 milligrams of scandium from each kilogram of bauxite residue, and in such a way that we can then produce a concentrate that can be used in refining scandium. So we have to go from the milligrams to kilogram scale to the grams per kilogram scale. And this is the same is true also for the other rare earths if you want to extract them. You cannot start with such a low concentration. You need to get grams per kilograms. And now there are two paths to follow in this way. One is to try and selectively recover scandium, avoiding the dissolution of all the other major elements found in the bauxite residue. This makes for a simpler process, but it will not achieve complete scandium extraction, obviously. And at the same time, it will not help you reduce your bauxite residue in terms of waste prevention and waste handling, because you would only be leaching a very small portion of the residue. The other path to follow would be to recover scandium along with the major metals. So this would require a complex processing flow sheet, which could achieve the full scandium extraction and reduce or eliminate the bauxite residue stream. So I will try to give a short review of various processes that have been proposed in this manner for extracting scandium and rare earths from the bauxite residue. One patented process which came very close to becoming industrialized was the Orbite process, which is a process for leaching, basically recovering alumina and iron oxides from bauxites and bauxite residues using hydrochloric leaching, concentrated hydrochloric leaching. Now, if you follow this extraction where you see you have strong hydrochloric leaching at about azeotropic conditions for hydrochloric acid, you're able to filter out the silica and the titanium phases, which are not dissolving. And then you have a solution that has dissolved 100% of the alumina and the iron and all the other minor elements in the solution. By injecting hydrochloric gas into the solution, you are able to saturate out the alumina as aluminum chloride, and then you can calcine the aluminum chloride into aluminum oxide. While returning back to your raffinate, you can do a hydrolysis to recover the iron, and then you are left with a solution that would contain the rare earths, the gallium, scandium, and all the other elements that were dissolved in the process. So, as I said, this process was never fully commercialized. So, another process, another group of processes, I would say, is the combined pyro and hydrometallurgical treatment. So there's numerous attempts in this, and we've done some also in our pilot test at Efthymios. So the idea is you do smelting to take out the pig iron, and then you have a slag which you will leach out with some mineral acid. So here you can get the total dissolution of scandium if you go above 3 Ns, and you will also leach out titanium and aluminum along with any iron that's remaining there. You have to be very, however, a big problem in these phases is the formation of silica gel. Especially if you go for a low liquid to solid ratio, you may end up experiencing silica gel formation. So this is a problem. You can see the slag produced from smelting bauxite residue has very little iron, but has very high calcium and silica, based also on the fluxes used during the pyrometallurgical process. So there is several variations of this idea, which is almost endless to track. A simpler process would be to digest bauxite residue with sulfuric acid, roast it, and then do a leaching to recover scandium and other elements. This is similar to what is being done in rare earth concentrates by Inobo. We have also the idea of alkaline roasting. Alkaline roasting was sodium carbonate roasting was a technology that predates the Bayer process for extracting alumina. So by using sodium carbonate, you can solubilize the phases that contain alumina in the bauxite residue to a point that you can recover them with simple water leaching. And then you have a residue, which is now free of alumina and soda and some silica. You do a smelting, you take out the iron, and then you leach eventually the slag to recover scandium and other elements. The other idea is to go for a smelting that would be specially conditioned for an alkaline leaching of the slag. So if you add enough lime to your slag system, you can form phases that are leachable in alkaline environments. So you can recover the aluminium from the slag, and then from the eventual residue, recover scandium. This is a variation of the Pedersen process, which also was tested as an alternative to the Bayer process many years ago. And finally, you can do reductive roasting. So instead of smelting, you can try to do solid state reduction and try to extract a magnetic fraction and then leach out the non-magnetic fraction first with acid to get silica and then with caustic soda to get aluminates. And eventually have a residue with scandium in there. So there can be, definitely this list is not exhaustive. There's definitely more flow sheets out there. But a key point in all of this, nothing has been demonstrated at a large enough scale. Most of these ideas come from lab scale experiments And so it's very difficult to say if they are really viable in upscaling, first of all, technically, and then also financially. So then we go to the selective leaching, which is less complicated. But as said before, we're not going to be getting the entire scandium value from there. So the idea is you go for leaching, you get a pregnant solution, which you need to go then to for impurity removal, which could be precipitation or ion exchange or solvent extraction. And then you get a precipitate, which you calcine and produce a crude scandium oxide. Now you can use various leaching agents. Most known, of course, is the mineral acids like sulfuric acid, hydrochloric, and nitric acid. There has been use of organic acids. There's reports, several papers on bioleaching, and some interesting work even on ionic liquid leaching. And finally, there's also a carbonate leaching, which I will explain a bit later. And all the studies here focused on changing the amount of acid, controlling the pH, the solid to liquid ratio, leaching temperature, and pressure and retention time. So here, the most important thing to look out for is that since we're having scandium in a very low concentration, we need to avoid the co-dissolution of the major elements like iron, titanium, and silicon, because they will interfere in the next step of the purification process. Silicon will not only interfere in the purification process, but it could lead also to gel formation. Iron and titanium are very, have close relations to scandium and will most likely be co-extracted during the impurity removal step. Therefore, you need to achieve a selective leaching against iron, titanium, and silicon. I mentioned before the carbonate leaching. So this is the pilot plant in Ukraine, operated by Rusal, which has a production rate of 200 kilograms of scandium oxide per month. This is a technology that has been developed by Rusal. It uses a mixture of sodium carbonate and CO2 to leach out scandium from the bauxite residue. It then proceeds to hydrolysis steps to remove some impurities and ends up with a concentrate of about 5% scandium oxide. The recovery of scandium from this bauxite residue is less than 30%, but it is a very attractive process in terms of capex and opex and simplicity. What's interesting about this technology is that, and it's something that one needs to keep in mind when discussing bauxite residue leaching, is that it's not universal. So the same technology was tested for the bauxite residue produced in Greece, and it didn't work. Why it didn't work? Because obviously this technology works on very specific phases that are within the bauxite residue for the Ukraine refinery, which are not present in the Greek bauxite residue. And this is something that somebody should keep close to heart, that the bauxite residues might seem the same in terms of an XRF, but are completely different in terms of XRD, and very much more so when you're looking to find trace metals that are basically associated with phases and are not having their own minerals. Another process is the acid direct bauxite residue hydrometallurgical treatment, where you go for acid leaching with dilute minerals at ambient temperature. You filtrate and you have a residue, you have a pregnant solution for further treatment and a residue for disposal. So in contrast to the previous Rusal technology, which operated in the alkaline region, a region that is more close to the alumina production cycle, now we're moving to the acid side. Here, scandium recovery, these are for the Greek bauxite residue, can go up to 40 or 50%. Iron recovery can be less than 5%. And aluminium, titanium, silicon are reported between 30 and 50%, while calcium and soda are fully recovered. So a problem with this method is obviously that we are leaching, that we are neutralizing first the bauxite residue, which is alkaline in nature, and then we start leaching the scandium. So we need higher reagent consumption. What's notable, what's in this from this work is that we see that there's a selectivity for scandium against iron dissolution. So nitric acid is more selective in this fashion, sulfuric acid afterwards, and hydrochloric the least. Yeah. You can see on the right hand a pilot that was designed in the 90s in the National Technical University of Athens by a chemical engineering school, where they designed and operated a multiple leaching cycle with nitric acid, where they even managed to reach 70% recovery using cycles of leaching, filtration, then elution of a specific resin, with multiple cycles. You see the flow sheet is a bit complicated on the right, leading to a final separation of scandium oxide and of phases containing, aqueous phases containing the other rare earths. Another idea was to use more exotic mediums for leaching. So like carboxylic acid, bioleaching, and ionic liquids. Again, the same process, we're just not using mineral acids. With organic acids, we get very low scandium recovery, and there doesn't seem to be much, let's say, merit to this. But there is a case of formic acetic acid that resulted even in up to 74 scandium recovery and similar aluminum yield. Again, of course, these are separate papers. It's very hard to compare between them. There are some bioleaching studies out there. These are just some mentioned here, using different types of reagents to recover 40 to 50 to 70, even 70% of scandium. And finally, there are some work with ionic liquids, which I'm very familiar with, where you can get up to 30 or 40% scandium recovery very selectively against iron, titanium, and silicon, or you can get up to 70% of scandium, but also with complete dissolution of iron, titanium. So on the right, you can see a pilot plant we did at National Technical University of Athens at the metallurgical school, where bauxite residue was leached with this task-specific ionic liquid HBET TF2N, where it has the added advantage that you can recover the ionic liquid at the end of the cycle. So you mix the ionic liquid with water, you leach the bauxite residue, you separate your solids, and then you strip the ionic liquid phase from the water and the scandium and the rare earths, and regenerate the eel. This has the advantage that you can increase, it works kind of like a solvent extraction in the last step, so you can increase by a lot the concentration of scandium. As we have managed to increase it up to 100 ppms, starting from a solution that had something like 5 ppms of scandium. Of course, the recovery of scandium still is 30%, 36%, but you are able now to have a solution that has much higher scandium and rare earth contents. And you can see some more details on this method. You can see the bauxite residue being leached with a mixture of water and ionic liquid. Then you can see the collected pregnant solution in the ionic phase. On top of that, we add some hydrochloric acid, concentrated hydrochloric acid, mix it, and you see now you have the regeneration of the eel. and the hydrochloric acid, which now has also the water content, much of the water content from the ionic phase. So this specific ionic phase has this miscible and immiscible switch behavior that allows it to be at center pH and center temperatures mixable with water, and at center others non-mixable with water. But you can see how less the volume of the new pregnant liquid solution is in the case of hydrochloric acid in regards to the ionic liquid. So we took that, we made a precipitate out of it, and you can see we got a precipitate that had 0.05% scandium and a bauxite residue, a leaching residue, a bauxite residue square, if you want, which was now enriched in iron and depleted in soda. This was a nice technology. We tried, of course, unfortunately, the price of the ionic liquid, even with the just 2-3% losses in each cycle, is so high that it makes the process uneconomic. So, with all this background knowledge, we came now to a project where we wanted to do a pilot scale demonstration of an acid leaching process for recovering scandium from the Greek bauxite residue. So we had all this knowledge about how many things we could use in terms of leaching, and we have to make a choice as to what we're going to use in our pilot. So first of all, we said for economical reasons, we will select an inorganic acid, as anything else seems to be driving the process very, very far away from any economical meaning. Then we know from the mineral acids that in terms of selectivity against iron, the trend is nitric, sulfuric, and hydrochloric. Here we will choose sulfuric because it's cheaper and easier to handle than nitric, but still more selective than hydrochloric acid. Finally, we will opt to use higher temperatures, which seem to favor scandium leaching in some conditions, and also in dilute solutions seem to accelerate removal of impurities like titanium, silicon, and aluminium. Of course, for the sake of economy, for making a viable process, we don't want to go into autoclave leaching. Therefore, we go at the temperature rate between 85 degrees and 95 degrees Celsius. And what is missing next in our quest is, of course, the technology that we can use to purify our pregnant leaching solution. Here we invested in a new technology by company 26. 26 is a global company that is a producer of scandium oxide, has a plant for scandium oxide purification, and they have developed their own patented resin that is, let's say, scandium specific and should be able to work in very dilute environments. So there's several patents around this technology, and this was our choice for partnering up the leaching with the impurity removal. So let's see a bit the leaching behavior of bauxite residue with sulfuric acid in the case of the Greek bauxite residue. And we did the lab test here with a very simple setup, starting with 85 degrees, 20% pulp density, and 4 hours retention time. And you see here the recovery of the various elements in relations to the kilograms of sulfuric acid per kilogram of bauxite residue. There are 3 different regions in this graph. The first one is when we have high scandium recovery. You see it's above 50%. We have silica precipitation. We don't have any silica in the solution because of the high acid. But we also have low selectivity. As you can see, that titanium is nearly at 80% and iron is nearly at 50%. This middle region, you see we don't have any markings in there. It's because in this region we form silica gel. So in this region we don't have enough. We dissolve all the silica in the bauxite residue and don't have enough acidity to drive it to reprecipitate. So this region is basically a region we cannot use. And then there is this very narrow region in the beginning where we get low scandium recovery or relatively low scandium recovery. We get, however, high selectivity in terms of iron and titanium, and the formation, the solution does not form a silica gel, even though it has dissolved more than 100 ppm of silica, but it seems to be in a metastable state, which can last for many, many days and could be a viable window for operation. So we have now pinpointed two operational windows, the yellow and the green one, and we will start investigating these two. It's also important to understand a bit what kind of PLS we're producing in these regions. So now you see here the major metals, iron, titanium, and silicon as parts per million on the left side, while on the right side you see parts per million of scandium. So even at the best we have just 14 ppms of scandium, while at the same region we have like 30,000 parts per million of iron and some 5,000 parts per million titanium. So in this green region we will get very low selectivity. In this red region we don't know, we will not get anything because everything has formed a gel, while in the yellow region we will get close to, we can even get up to 10 ppms of scandium, and you can see that the iron and titanium are below 1,000 parts per million. And if you're wondering what is the scale in terms of molarity, we are discussing here from half molar sulfuric acid up to 3.5 molar sulfuric acid solution. So we went to the green area and did our first campaign. We extended the leaching time here with a 3 molar acid solution from up to 100 hours, up to 96 hours. And you can see the trend of the various elements. You can see that if we spend 96 hours of leaching, we can get almost 85% of the scandium out, which still is just 12 parts per million in terms of pregnant leach solution. So the data labels indicate the concentration in parts per million, while at the same 96 hours we will get close to 50 grams per liter of iron, so complete dissolution of iron as well. You can see that what we said in the beginning, with high temperature and extensive time, you can see that titanium dissolves and gradually reprecipitates out of the solution, and similarly to silicon, although the trend is much more small. But you can see that titanium hydrolyzes out of the solution in this pH. Alumina is leached about 40%, again giving another 10 grams per liter of aluminum in the solution, while titanium at the lowest point is just half a gram per liter. So we took this pregnant leaching solution and tested it with the sear resin. So here these are the loading graphs of the resin. The x-axis is the number of bed volumes. So you have a column packed with this resin, and you start passing the pregnant liquid solution through this column, and you measure the exit of the resin to see what's the concentration in scandium, iron, titanium, and you measure the number of bed volumes that will pass through the resin. So you can see that in this pregnant liquid solution, we have a very low loading capacity for scandium. You see, after 15, 20 bed volumes, the resin can no longer add more scandium. It has just loaded about 60 milligrams per liter of resin, while at the same time it holds more than 14,000 milligrams of iron per liter and 25,000 milligrams of titanium per liter. So in other words, this does not work for such low scandium content and such high impurity in the pregnant liquid solution. So this drives us into campaign 2 to test the green area where we will get lower impurities. So this test here presented is at 1 molar sulfuric acid, 95 degrees and 20% pulp density. Here we don't need to extend the runtime more than 1 day. You can see that the difference between the first hour and the 24th hour, scandium is relatively stable, while silicon, which initially, as I said, forms a metal stable phase, you can see with the passing of time and the retention of high temperature drops, the major drop happens around 12 to 16 hour, drops from 4,000 parts per million to about 400 or 500. Similarly, titanium slowly precipitates a bit out of the solution, but not remaining around 500. And iron is very low. Oh, sorry, I think I said it the other way around. Iron is around 500, titanium drops to about 9 parts per million. Yeah. So we tried this with the resin, and here you can see we did different tests. So the hollow diamonds is the pregnant liquid solution at 1 hour, so the one that has more impurities. And then we have the pregnant liquid solution at 16 hours, which has the fewer impurities. You can see that again, we got to 500 milligrams of scandium per liter of resin. So we got up by 10, by a factor of 10 in relation to the previous campaign. But still, we got a high loading of titanium and iron, iron being re-released after some bed volumes. To understand a bit better, there's also the test with the black circles. This is the same PLS as the 16-hour, but it has been spiked with scandium to see if the resin works in this region or not. And as you can see with the spiked scandium, so instead of 7 ppm, we now have 60 ppm of scandium into our solution. You can see that the resin responds much better and exceeds the 2,500 milligrams per liter, indicating that the problem we have is that the scandium concentration is too low, again, in relationship to the impurities in the solution. So we had to think of ways of getting even less impurities in the solution. So we tried even lower acid concentration. And here's an experiment where using 0.4 molar sulfuric acid, 85 degrees, 20% of density, 1 hour of leaching. But what we're doing, we are reusing the pregnant liquid solution that we produce after one leaching with some extra acid into a second and a third step of leaching. So as you can see here, this allows us to get in 2 steps all the way to get up to 8 parts per million of scandium, while iron and titanium remain relatively low. Even a third cycle could be used, but third cycle, you see, we start losing in leaching recovery of scandium, so it doesn't seem to be needed. So this was the third campaign of two leaching cycles to get a relatively high scandium pregnant liquid solution with low iron titanium. You can see here the results of the resin testing the pregnant leach solution, 2 different PLS solutions for 2 cycles. So you can see that in the first cycle, the resin reached 5,000 milligrams of scandium per liter, which was an amazing result. And then to verify that the resin can be reused, a second cycle was done, second loading cycle was done, and we got similar results. So this is a very impressive performance by this resin. It took 200 bed volumes for the resin to reach its breakthrough point. Breakthrough point meaning the point after which it starts losing a part of scandium. So this new graph I'm introducing on the bottom right side is the relative concentration of the raffinate coming out of the ion exchange column. So we start seeing some scandium in the raffinate after 200 bed volumes, and around 900 bed volumes, the resin is no longer retaining any scandium. All the scandium that goes in goes out. So yeah, this means you can still operate. It does not mean that you need to operate 200 bed volumes. The way you would operate this, you have a series of columns and scheduled in such a way that when the first column reaches the exhaustion point, there is a number of other columns that are still collecting the scandium, and then you elute the first column, and the cycle continues. So it is feasible to do leaching, to do scandium extraction at this level of the exhaustion point. These are the other elements, iron and titanium, in the similar graphs. You can see that titanium did not go that high. It's just 4,000 milligrams per liter, and iron was 12,000 milligrams per liter. And in the second cycle, both elements were collected less. So after we loaded the resin up to the exhaustion point, about 900 bed volumes, the resin was washed and eluted in order to get a scandium pregnant solution, which was precipitated into a crude scandium concentrate. And this concentrate had 25% elemental weight of scandium, 0.1 of iron, and 5% of titanium. So we have managed from a bauxite residue containing less than 0.1 grams per kilogram to go to a concentrate that contains 250 grams per kilogram. That's 2,500 times an increase. And this is the first viable candidate for recovery scandium from bauxite residue, right? So since we got to hundreds of grams per kilogram, this can now work with the established solvent extraction processes to produce pure scandium. So that was the lab results, but we set out to do the upscaling to see if this actually works. And so this is our leaching pilot at Efthymios in Greece. It has several reactors. Basically, we feed into a pulping reactor, a bauxite residue. The bauxite residue goes in a pulp of 40% into the leaching reactor, where it's contacted with concentrated sulfuric acid at 85 degrees. And after a retention time, it goes to a holding tank, and from there to the filter press, where we separate solids and liquids. It was very essential for us. Yeah, here also you can see the first time we saw a clear liquid solution coming out of our filter press. It was very important for us to translate the process in an industrial viable process. So instead of this 2-cycle, we discovered that we can get equivalent results if we double the pulp density, something that we can do in a pilot, not so easy in a lab scale. So we work at 40% pulp density, 1 hour retention time, and even did a sort of small experimental test with different acid to bauxite residue inside the pilot. And you can see again, these graphs are very similar to the ones presented in the beginning of this presentation. On the yellow side, you can see the spike, how scandium goes up, how iron is very low and then picks up after 0.3 kilograms acid per kilogram bauxite residue. So if you look at these results, you will see that at 0.28, we are getting very similar results as the two-cycle approach that was studied in the lab scale. This means that we have a recovery of close to 30%. But if we go a bit higher, we can go, you see there's a huge incline where you can get 50% of scandium, but at the same time, your iron is doubled and your titanium is tripled or quadrupled. Therefore, this is a very steep increase, which is also threatens to throw away the results of the resin. In our pilot plant, we are able to process 250 kilograms of bauxite residue in a single shift, producing around 400 liters of pregnant liquid solution. And our target for the leaching was to produce enough pregnant liquid solution to do at least 2 cycles in this ion exchange 2.6 pilot plant, which is also installed in Greece. So we're housing it for this project. This pilot plant has 3 15-liter resins. Our goal is to reach the breakthrough in one of these resins and produce the concentrate having close to 25% weight. At the moment, we have done the leaching and we are currently in the first days of passing our solution through the resin. So unfortunately, I don't have results for you yet, if we will get to the 25 or not. But I can tell you that we are very close in the targets, the concentrational targets that we set out to get. And we have leached by now almost 10 tons of bauxite residue. Is this a viable option? Okay, so these are very preliminary numbers, but we managed to take down the acid needed for this process all the way down to 0.3 tons of sulfuric acid per ton of bauxite residue. That's about 13 kilograms of sulfuric acid for each gram of dissolved scandium in the PLS. So the cost of the process is driven mainly by the cost of the sulfuric acid and the cost for heating up the solution at 85 degrees. You can see a very draft estimation based on this other technologies that will live up to the production of a master alloy, where we have done a theoretical calculation that from 1.4 tons of bauxite residue, we would produce 1 kilogram of aluminium scandium master alloy, 2%. And 60% of the operating costs would be related to the leaching step, and primarily to the energy involved in this leaching step, and then to the sulfuric acid, as you can see in this graph below. Still, we estimate, even with this very draft calculations, about 40 euros per kilogram for the aluminium scandium alloy as an operational, only on operational costs, excluding personnel. And as I said before, the price for this is 100 to 150 kilograms, dollars per kilogram. But you should expect that once you start a mass production of this alloy and there's a mass demand, the prices could be as low as 50. So there is room, not huge room to celebrate, but there is still a viable window there. And what's more important is to understand that there's a significant cost reduction to be have when this process is integrated in the buyer process. So this is a very simplified view of the buyer process operated in all the alumina plants. you have on the left side the Bayer cycle, at the point of which you have the creation of the red mud with the slurry, which goes for, after clarification, goes into a series of washers, and either ends up in a dam or a filter press in the case of our plant. So for simplicity here, imagine you see two washers. Usually plants have 5 or more, where you have a counter current introduction of water from the last washer all the way going back into the Bayer process, this water, and the slurry goes is gradually washed until it gets to the filter press. So what's interesting here is that the system, the clarification step, is already in high temperature. The slurry exits enters the first washer at a temperature of above 100 degrees sometimes, and it exits the last washer at temperatures of 45 to 50 degrees. This loss of heat is mainly due to the fresh water added in the beginning in the last washer. So we can imagine how we could intervene this scale leaching process just after the last washer and before the filter press. Basically, you would add another reactor there that would have the same capacity as the washers. And in this reactor, you would do sulfuric acid leaching, then drive everything to the filter press. The filter press, the filtrate, instead of being remixed with the water in the last washer, it would constitute the pregnant liquid solution out of which the shear process would take out the scandium. And we can imagine that we can optimize this process greatly if we, instead of adding cold water, we added just hot water. There is a lot of heat exchange capabilities inside the Bayer process. So we could eliminate a significant amount of energy for this process. And also the small retention time, we're discussing about an hour leaching, means that you don't need a huge reactors. You just need to have another washer next to your last washer, basically. And what about the rest of the bauxite residue? So our process dissolves any significant fraction of bauxite residue. In fact, as it precipitates calcium sulfates, it marginally increases by 2% the weight of the bauxite residue. But the filter cake produced is now depleted of soda and it's very high enriched in calcium sulfates. This makes it a very interesting raw material for cement production. You can see at the XRD to the right that we are missing all the phases that were created during the Bayer process, the secondary phases, like cancrinite, catotite, and calcite. And we have as a new phase, basanite, which is expected. And at the same time, we are able to see that some of the original peaks from the bauxite ore, like the diaspore peaks, are now much more prominent. So efficiently, what we have done is washed away the secondary precipitation from the Bayer process. In terms of an XRF composition, you see it at the bottom of the screen. I have to say that this was one of the first filter cakes, so it has a high sulfuric presence. It's the 16% is not, after we experience a bit more with the filter press, we know how to wash it better, and now it's close to 6-7%, not 16. But again, we have a filter cake that's enriched in iron, seems to be enriched in alumina because it has practically lost a lot of its weight, and it's depleted in soda. So we have taken away the major drawback of reusing bauxite residue, which is its alkalinity. So here's a list of references throughout this presentation, and I'd like to thank you for your attention, and I'm happy to answer any of your questions. I have to point out that this research was part of the SCALE project, which was funded from the European Community, and of course, it was not all me. It was a cooperation between Efthymios, 26 company incorporated, and National Technical University of Athens. Thank you very much.
Thank you, Doctor, for such a detailed presentation. I think before I go any further, I've seen there are a number of questions in the question and answer section. So I'll probably, what I'm going to do is I'm going to read the question and then you can respond.
Yes.
Okay.
Yeah,
First question is from Nikhil Dhawan. Is there any particular reason why scandium is associated with iron minerals? What about titanium?
So iron and scandium have relatively the same ionic radar. So
Okay.
that is why that's why it's such a problem to separate iron from scandium also.
Okay.
In fact, most resins require that you reduce the iron 3 to iron 2 if you're able to separate them. So the main problem is their close relationship. It is also found in titanium phases. So there are reports about the perovskite phases that have scandium in there. It's very hard to tell because when using techniques like laser ablation, stuff like that, you cannot separate titanium from scandium. You cannot distinct them in this type of measurements. I think it's mostly iron, more so found in iron and less so in titanium. But of course, in some cases, you have minerals that have both iron and titanium presence.
Okay.
So in this case, it's also related to titanium.
Okay.
Yeah.
All right. Thank you very much. Then the next question is from Kevin Smale. Is beneficiation via WIMS a possible pre-concentration step for? I think this applies to bauxite, taking into account that it contains significant amount of iron.
Yeah. So I mean, if you're able to do that, I think the alumina industry will give you a lot of money because they don't care so much about scandium. But if you're able to take out the iron from the bauxite, you would be solving the bauxite residue problem because 40% of bauxite residue is iron. And also you would be increasing dramatically the productivity of an alumina plant, right? Because we are now feeding it with mineral concentrate, the bauxite ore at best has 60% alumina and 20% iron. And it's a lower quantity, a lower quality, it has even more iron. So there has not been anybody that has succeeded in industrial scale to beneficiate iron out of the bauxite without smelting it with beneficiation technologies, because bauxite, they're very fine particles and it doesn't seem to work.
Oh, okay. I think
the liberation degree is very small. It's very fine particles in the bauxite, the iron and the alumina phases, and in the end, it seems not possible, or nobody has achieved it, to liberate it through a simple beneficiation process to separate iron.
Okay. Now, thanks very much for that, for the clarity. And the next question again is coming from Nikki Dhawan. Is there any specific reason why roasting should be carried out at 700 degrees Celsius? I think this applies to one of your flow sheets, Doc.
Yes.
Is this the same? Sorry, is this the same as acid baking in the first step, where there is sulfuric acid digestion followed by roasting?
Yeah.
I'm not sure if I'm not sure if the question is clear to you.
So I can for sure understand the first question. Why should we go at 700 degrees for sulfuric acid roasting? Yeah.
Yes, please.
Yeah, you don't need to go to that high. This was the reference from a specific paper. In fact, I've recently seen another work that has done it at lower temperatures. I should have perhaps updated this point there. There is a recent paper out from a team in Canada that do it around 400 and have studied in detail the kinetics of this roasting process. So yes, this was just a reference from the work that we cited. I don't see a reason why it should be at 700. Again, maybe it would depend on the mineralogy of the bauxite residue used.
Of the bauxite, okay. No, that's very interesting. And I think on the acid baking, on the sulfuric acid digestion there, or the, the Bayan obo, they mix the rare earths ore with sulfuric acid and then bake around 300 or so degrees Celsius.
Yeah.
Is this the same that you highlighted on one of your?
This is more or less the same idea. I have to look up really why this person wrote about the 700 if they explain it for some reason, but yeah, the idea is anyway some sort of baking process, right? And then followed by leaching. So yeah, it could be at lower temperature.
Okay, so that we can say that's the more or less like scandium also is amenable to the acid baking followed by water leaching like other rare earths or
yes.
Other. Okay. No, I'm sure if Nico would like some more clarity, he or she will get can send an email through the organizers, and then we can link you guys for further clarity.
Yes.
Okay. The next question is from Carol Taylor. When should geoscientists start looking out for new current kid on the block, that is scandium? I think this is directed at field geologists at the exploration phase, or concentrator, or smelting and refining phase. So,
well, I think we know it's known scandium is not so under the radar. I think for geologists, geologists love to talk about the entire periodic table. So it's not so under the radar. It is the fact that you don't find any minerals for scandium. So I definitely think that at the exploration phase, it will have to do with what other. It cannot be a scandium resource, right? It will have to be a bauxite that after processing it, you have a chance to recover the scandium. It will have to be a nickel laterite, cobalt laterite that also contains a high scandium. So it comes as an added value, an added byproduct, not as your primary target. Or it could be okay in a rare earth deposit along with the other rare earths. But even in rare earths, as probably I think the group knows, is that most of the time it's not a single metal operation. You like the Bayanobo, you first recover iron and then you recover rare earths and so on. So it's scandium is very rare earth in this aspect. You will not try to mine it on itself. Definitely, there is no way to concentrate in terms of minerals. At least I haven't seen anything around there that you can do a mineral beneficiation and come up with a scandium concentrate, unless this is a rare earth concentrate, which includes scandium to some extent.
So in a way, we have to considering scandium production, we're looking at it as a byproduct from the production of other maybe major minerals like nickel and cobalt in the case of nickel cobalt laterites.
Yeah. I think nickel, as I said in the presentation, nickel cobalt seems to be the gold opportunity here, right? Because nickel and cobalt are in high demand and will be in high demand.
Yes.
So adding scandium there, another niche element, is just will make it even more feasible.
That's interesting. I think we should start looking for more nickel cobalt laterites that contain scandium. Okay, then the next question is from Carol Taylor again. Are the laboratories able to deal with scandium detection on a sample scale? I think this is due to the fact that we've talked so much about the low scandium concentration in the bauxite residue and also in other geological samples.
You definitely
dealt with the detection limits. I'm sure this is more on the lab analysis aspect.
Yeah, but you definitely cannot pick it up with an XRF, right? You need to go into a wet chemical analysis, fusion, ICP methods, and so on. I think this is similar to the other rare earths. Rarely you will get a rare earth reading on an XRF. Maybe perhaps some cerium, but you will not be able to see the other ones. So you need to do a fusion and a leaching, a fusion and an ICP measurement. You don't get a lot of problems if you do that. You will find this above 50 ppm, so it's not a problem.
Oh, okay. Okay, I hope, Carol, you have been answered there. And again, from Carol, after recovering scandium, do other elements add to a worthwhile total basket value in dollar terms as co-products? I'm sure this is specific to I think the second or last slide where you were actually giving us a financial breakdown based on scandium only. What about the other elements as well?
So this is a good question, actually, because I was intended to speak on scandium and rare earths, and I ended up being a bit more scandium focused. So as I showed, for example, in the bauxite residue, the Greek one, you have about 100 ppm of scandium and 100 ppm of neodymium. But the price difference between scandium and neodymium is huge, right? Scandium represents 95% of the value of all the rare earths in there. It doesn't seem worthwhile to go after the neodymium and the yttrium, or the lanthanum and the cerium, or even less so. In any case, of course, this is something we wanted to do and wanted to look into. And there have been previous studies like the one I showed with the ionic liquids, where indeed, if you could co-extract the rare earths after the scandium extraction. So again, scandium separates itself from the solution. It's easy to precipitate out scandium and leave the rest of the rare earths inside. So it's a fairly easy separation. In the case which I just detailed with the sulfuric acid, we are losing the rare earths inside the gypsum we're forming, right? If we wanted to pick up the rare earths as well, we should go for hydrochloric acid leaching, which would allow us not to precipitate as double salts the sulfuric acid, the rare earths. And after the ionic change in the raffinate, you would still have some parts per million, around 10, 12, 15 parts per million of neodymium, yttrium, and so on. So, although still, that would be a very poor pregnant liquid solution for rare earth recovery. You would have to probably go again into another ion exchange or other type of technology, even more experimental, to recover the rare earths. I don't think it would be value for money to do that.
Okay, no, thanks. Thank you very much on that. Again, I think we have one from Nikhil Dawan as well. Do you think acid baking can facilitate the structure breakdown of bauxite residue phases to facilitate extraction?
Yes, definitely can. I've seen two types of, there is the acid baking, and there is also another technique performed in Germany, in Aachen, which is sort of pulp leaching. So I've seen it also mentioned as water deprived leaching, where you add a lot of acid with very little water, and you raise the temperature to a point where the water basically evaporates. Both of these techniques break down the structure, and you're able then to leach out the rare earths. I think there's an exceptional paper on this acid leaching, or this acid baking bauxite residue from the Toronto University.
Okay.
The professor is Giselle Azimi. I don't remember Frank is the name of the PhD student, but I think if you search up Azimi, you will find this publication.
But is that sorry, Doc, is that paper part of the on your reference list?
And I think no, it's not. I'm
Oh,
sure
okay.
This was very new to me. This was.
Okay, no, it's fine. If there's someone who's interested, we can always get in touch and link you up.
Yeah. Yes.
Okay, thank you. The next question comes from Itmelen Tobadi. She says, from an EU perspective, what is more critical between scandium for aerospace applications and rare earth elements for renewable energy applications. I noticed a lot of work on scandium recovery at the areas. I think this is the European conference 2020, done on rare earth. So she wants to see where the focus from EU's point of view. Is it now on scandium and less of rare earths, or?
Yeah, I think that there is the region was a bit economic to start with, and it's still economic. So back in 12, 13, when the huge rare earth prices exploded,
Yes.
The prices went high up. Everybody then was predicting that the world is going to run out of neodymium and we will not have magnets. And all these doom scenarios, and all these doom scenarios were supposed to happen around 2016. 2016 came and went, and we saw all these junior mining companies starting up new mines, then going bankrupt as soon as the prices went down again. And so today, you don't have the same problem. You still discuss with the criticality of the rare earths, but after, I don't know, 6-7 years of research on rare earths in Europe, it became evident that there is nobody willing to invest in making a huge rare earth separation facility in Europe. So even though there is a huge deposit in Greenland, which is considered Europe, should be considered as well the North America, I don't know, that is going to be producing rare earths very soon, they will be sending the concentrate for refining to China. So it's not just a matter of finding rare earths in the ground and extract them. It's the rest of the industry which is not present in Europe, and for that matter, present in any other place of the world. It's mainly all in Asia right now. So in Europe, you have a lot of companies that are making magnets, so they just need the end product, the neodymium and the praseodymium, or catalysts. So you need the final oxides, not this intermediate step. So as long as you don't have this as an industry, you will never, the research also died away a bit, because we looked at all the deposits, they made maps, and then they looked at all the e-wastes and the lamps and everything, made a lot of pilots, publications, and after a while, if there is no industry to back it up, to take it up and start producing, there is not much more research, I think, in this field. Whereas scandium happens that it's something that's emerging, right? And it still has a lot of ground to cover before it is it's made into an industry before it scales up. So that's probably the difference why scandium is still around and rare earth research is a bit falling behind in Europe. This is a very sad problem, which we have seen in the past, and it's repeating again. Sometime in the 80s, there was huge knowledge in the European in Europe on rare earths. There was a lot of industry there, and slowly this business went away, and with it went away the knowledge.
Exactly.
So today, in this last decade, we have again huge knowledge of rare earths. We have dozens of laboratories across Europe that are able to analyze rare earths, which was not the case 10 years ago. You would not, the question asked before, a while before, you will not be so easily to find somebody that can analyze scandium or neodymium 15 years ago. Today, it's fairly standard. Everybody, all the universities have at some point found some rare earths that we need to analyze. So all this knowledge is available now, but I'm afraid in the next 5-6 years, it's going to die away as well.
Yeah, I think thank you for the clarity. I think the same problem that the EU is facing is also what we are facing here, particularly in Southern Africa, and in terms of having all these massive rare earths projects, but then struggling to stimulate the downstream industry or even the production from those projects. They're still just projects. But I think we'll be talking about that in a separate event, which is the Rare Earths Conference in October this year. So the next question again is from Christoph. In which concentrations do we find lanthanide, cerium, and erythrium in the bauxite residue, which you mentioned? Does their value justify a Pyro Hydro metallurgical extraction similar to scandium?
Yeah, as I said before, it's mainly light rare earths we find in the bauxite residue. So it's, I don't know, 400 to 600 cerium, 300 parts per million to 400 lanthanum, and around 100, 150 yttrium and neodymium each parts per million. So it's yttrium and neodymium and scandium seem to have more or less the same amount, and lanthanum and cerium more elevated. But really, only yttrium and neodymium might have some economic value. And as I said, this is too small for this question. This comes from the geologist when they see that we have 1,000 parts per million total rare earth. They say this is a value resource for rare earths because that's the same approach when they do in a mineral, in a metallurgical ore, right? But the difference is that there is no beneficiation here to be done. So start with his 1,000 total rare earth oxides, but you cannot up-concentrate it with a mineral beneficiation since you don't have hosting minerals to separate. Therefore, it does not work. This was done in the URARE project, and you cannot, you will go into chemical processing, Pyro Hydro something. And once you start to go into that, you will end up with a very dilute stream at some point, and you will need a very high-tech solution for extraction. No, so that's the problem. Okay.
Yeah, I'm sure, Christoph, your question, I'm sure you got answered. Then from Evelyn Manjengwa, she says, out of interest, what is the implication of adding scandium recovery after the bare process? I refer to the diagram you presented where scandium can be added. I'm not sure about that on the environmental life cycle performance of the entire. Okay. So I think she wants to know one of, I think should be your last slide or second from last slide where you coupled the scandium leaching process with the bauxite in terms of the life cycle performance of the entire system.
Yeah. So one thing, the way I showed it, it seemed to be changing nothing because we will still be producing out of the filter press a bauxite residue. In fact, this bauxite residue will be a bit better. It's not going to be alkalinic. It's going to be a neutralized bauxite residue, which could be uptaken by the cement industry a bit more easier, and definitely stored with less problems, right? Since we don't have any soda anymore there. On the other hand, of course, I stopped the process at the sear extraction, and we have not seen anything about the raffinate. So I told you we produced some 12 to 13 cubic meters of pregnant liquid solution to pass through these 15-liter columns. We will extract the scandium, but we're still going to be left with 12 to 13 cubic meters of raffinate. So that will be scandium depleted, but it will still have acidity and it will still have the other elements like soda and aluminum in there. So unless this is something to be done to see what we do with this raffinate, how we can return it into the leaching process. Otherwise, we have a huge environmental problem, at least in Europe. There is no way to, you will have to start adding lime to neutralize everything until it's made into water that can be safely disposed. This would mean adding lime, of course, means adding CO2 to your process and so on. So therefore, it could be a burden in terms of the raffinate unless the raffinate cannot be recycled into the process. Other than that, it will not add any real problem in terms of energy consumption. It doesn't add a lot. In terms of acid consumption, as I said, it's 0.3 per ton of bauxite residue, so it's not a huge amount.
Okay.
Yeah.
Thank you for that. And I think this is the last from the attendees. What is the host mineral for scandium?
That's a very difficult question to answer. As I said, it's mainly found. I mean, there's a PhD thesis that found it high concentration of scandium in goethite grains and hematite grains. So that could be in the case of the bauxite residue we're looking at. It seems to be in the iron phases. And if you look back at the slides I showed, you can see that when we got 80% scandium extraction, we also got 95% iron dissolution, right? So it's a definitely link between these two phases. On the other hand, when in the area that we are leaching, we seem to be leaching out very little iron. So we believe that there is a portion of scandium that is that has dissolved in the Bayer process. It has reprecipitated in this secondary phases. So we are probably leaching some of that or all of that, plus some of the scandium in the iron, but a very little portion. But that is that's not a host mineral that I can identify. Say it's
okay. I think yes.
I can say also that yeah, there are some phosphates inside the bauxite residue, and from time to time, some people have claimed that that's where the rare earths are, and there are some other studies that speak of carbonates, and that's the place where rare earths are. So these are all studies of somebody in a microscope finding a single grain and saying, okay, I found a carbonate grain and there are rare earths inside.
Yeah, I think thank you for the clarity. I think it's a question that we can say, you know, to all mineralogists and geologists out there, please help us identify how you know, the host minerals for scandium. Because once we know the host minerals, we can find a way to take it out. Then I think this is the last question from the attendees, but I have one or two questions. Let me stick to one. In our process flow sheet, the final financials that it presented are based on bauxite leaching. Was there a study that goes via the slag, take out the iron and form slag, and then what would be the financial metrics look like if you go through that route?
So that's our current, we're running in parallel different projects, and that's one of them.
Okay.
But we know from the past that when we try to do something that's simpler, we take out the pig iron and then form mineral wool with the slag. The pig iron production in the electric arc furnace amounted to a pig iron that could be a steel scrap substitute because it had also silicon, titanium, chromium in there. And so it had a fixed selling price as steel scrap. And that amounted to just 30% of the OPEX of the EF processing. So this means that you need to make the rest of the set from the value that you will get out from the slag. Now, it is questionable if by leaching the slag, again with the sulfuric acid, for example, you will get so great results. I mean, we know that we can get 100% scandium extraction with leaching the slag at about 3 molar acid. But again, we just get a 20 something parts per million scandium in the pregnant liquid solution. No iron, which is a huge benefit in terms of this resin problem. But still, we're just around 20. It's not like we get to 100. So we will keep working on it and see if it makes sense. On a first level, it does seem to be not so practical unless you do an even more complicated flow sheet where, for example, you take out alumina first from the slag and then you take out the scandium. So, but the more steps you add, the more difficult this becomes to realize, right? Because industry is not looking for building 5 new plants. right? It's looking for simple ideas that they can put on to their plant.
Okay. All right. No questions from me. Is there anyone from the panels who would like to say one last question before we close off? Just one. You can raise your hands. Okay, I don't see anyone raising their hands. So before I close off, I would like to thank Dr. Efthymios for this very, very incredible presentation. Thank you for that. And I would also like to thank everyone who has attended the webinar. And I would also like to point that this discussion is just beginning. This is the beginning. We're not done yet. We are organizing a conference in 18th and 19th of October this year, where we're going to talk a lot more on the rare earths, now focusing on the Southern African rare earths projects, Southern African rare earth deposits, the mineralogy, the complexities, and also how we can integrate, with the upstream and downstream, manufacturing in Southern Africa, not only South Africa. So I think this is just the beginning in terms of discussing talking about the rare earth elements, including scandium. We know now it's not an easy walk in the park. So from me, I would like to say, Dr. Efthymios, thank you for such a wonderful presentation. I know I've taken almost 1.5 hours of your day already. So thank you for that. And I would like to give Butle to say one or two words. Is our link with you. Butle, are you there?
Yes, I'm here. Thanks, Dr. Matinde. And of course, thanks, Efthymios, for such an inspiring presentation. As always, when you present, I'm always inspired. Thanks. And of course, looking forward to more results from your test work, both the Pyro and the Hydro. So, of course, I'm very interested on the pyrometallurgical work. So I hope we'll be discussing more in the near future. And it would be nice if your team could also participate at our conference in October. And thanks a million times.
We'll try.
And all the best.
Yeah. For sure. Thank you very much for having me. Thank you, Elias. Thank you, Bule. Thank you to all the organizers, and thank you to the people that sat through this and posed so many nice questions. It was a pleasure for me.
No, the pleasure is ours, Doctor. So I think with this, we can close off the webinar, and we will be requesting your presentation. I hope that's okay with you.
Yes.
And we'll be circulating the presentation as well. No, thanks very much. Thanks for gracing us with such a wonderful presentation. Enjoy the rest of your day. Thank you.
You too. Have a nice
Bye, everyone.